Kia ora and welcome to this video on question 5 of the 2016 Scholl Calc exam. After question 4, this one's definitely us back down to earth. Part A is a complex numbers question. Part B, linear programming, and Part C, networks, or critical path analysis. It has been a while since these two standards appeared in scholarship, two of the smaller internal assessments, and it's also been a while since I've had an option in the exam to do one or the other. Okay, but we'll go through all three in this video. Alrighty, question A asks us to first up find the roots of z to the 11 equals 1. So this is a merit question where we use de Moivre's theorem to solve it. Graphically, the real solution is 1. Okay, so if z equals 1, there's clearly a real solution to this. But there are 10 other solutions that are all spaced evenly around the origin. So the distance between the solutions is 2 pi over 11. And just so I can get my diagram roughly to scale, 2 pi over 11 is 32.7 degrees. So Z2 would be here. Z3 is about there. Z4 is just over 90. Sorry, my bad. Z3, Z4, another one's 130, about there. Another one 163. Then down here, z to the 7, z to the 8, z to the 9, z to the 10, and z to the 11. So all the solutions are equally spaced around the origin, and they're all 1 away from the origin. So if we solve z to the 11 equals 1, the first thing we do is turn 1 into polar form, or 1 is just 1 cis 0. And then we take the 11th root, z is 1 cis 0 to the power of 1 11th. We use the theorem, in this case 1 to the power of 1 over 11 is just 1. And 0 divided by 11 is just 0. So we get 1 cis 0, which is 1 again. That we get the first real solution. And then the other ones, Z2 is 1 cis 2 pi over 11, because we add an 11th of a full circle. This angle here is 2 pi over 11. Z3 is cis 4 pi over 11. Cis 6 pi over 11. Cis 8 pi over 11. 10 pi over 11. Now at this stage I could go 12 pi over 11, but instead of 12 pi over 11, which is the z to the 7 one down here, I go backwards with my angle and write minus 10 pi over 11. And then I work my way backwards. Minus 8 pi over 11. It doesn't matter, if you'd written 12 pi over 11, we would have had to convert it anyways to be able to solve the problem. And then the last one, minus 2 pi over 11. Now the original equation had no complex numbers in it, or no imaginary numbers in it. Z to the 11 equals 1. All the coefficients are real. And that means that the conjugates will always be solutions. So you can see here that apart from the real number 1, which has got no mates, Z2, the conjugate is Z11. Yeah, they've got the same modulus, but their arguments are negatives of one another. And in the Argonne diagram, hence why I was trying to draw my thing to scale, z2 and z to the 11 have the same real part, but they have negative imaginary parts. Remember, the real axis is this and the imaginary axis is that. So they have the same real part, but the imaginary parts differ by a minus. Okay, so if we add up all of the solutions to this problem, z2 plus z11 is equal to 2 cosine of 2 pi over 11, because we get two lots of the real part when we add. z3 plus z10 is going to be 2 cos 4 pi over 11. z4 plus z9 is going to be 2 cos 6 pi over 11. z5 plus z8, 2 cos 8 pi over 11. z6 plus z7 is 2 cos 10 pi over 11. And the other thing to note is that when we have an equation written in the standard format, z to the 11, I'm going to write plus 0 z to the 10 plus all the way down to minus 1 equals 0. This coefficient here gives us the sum of the roots. And because that term isn't there in the equation, it's just z to the 11 minus 1 equals 0, the sum of the roots must equal 0. So if we take the real root 1 and all of these dudes here and add them up, we get equal to 0. Therefore, 1 plus 2 lots of cos 2 pi over 11, cos 4 pi over 11, plus dot dot dot, should have done that a lot earlier, cos 10 pi over 11, all of that adds to 0. If we move the 1 to the other side and divide by 2, we've got our proof. Of which you can chuck it in the calculator and check that it works, but it was a proof, it did tell us the answer. So the important thing in that is to realize the connection between the cosine, being the real part of a complex number, and the cis, which was the actual solutions. Alrighty. Another way of thinking about it would be just to look at the diagram there and just adding up all the solutions. All the imaginary stuff disappears and we're just left with two lots of this height. No, not that height, my bad, because that's the imaginary part. You get two lots of this length, which is 2 cos 2 pi over 11, and then you get two lots of the z3 and z10 adjacent side, and so on. And all of those cancel each other. Okay, part B. Students to sit an exam. What a question to have in the middle of an exam. The questions are divided into 3 groups, and the student may answer any question from any group so long as the total number of questions answered does not exceed 100. So the teacher doesn't want to mark too many. Easy, group 1, group 2, group 3. So we'll call these X, Y, and Z questions. The total number of questions does not exceed 100 is X plus Y plus Z must be equal to, less than or equal to 100. We've got some time in there. Each question takes a different amount of time. The total time available for the student is 3.5 hours, which we can convert to minutes. 3.5 hours is 210 minutes. So this time constraint tells us X. Just slightly changed my blue, that's going to be annoying. Where's the time? Time to time. 2 minutes per question for group 1, 3 minutes per question for group 2, 4 minutes per question for group 3. So 2x plus 3y plus 4z. That's the total amount of time needs to be less than or equal to 210. It's another constraint. Groups 1 and 2 are the most mechanical, and the student can tolerate only 150 minutes of those. So that's 2.5 hours just of the questions in group 1 and 2. So x plus y. The total number of questions answered in those groups must be less than or equal to, oh no, we need to also factor in time. Two x plus 3y less than or equal to 2.5 hours, which is 150. Okay, although nice, they gave us one of the constraints. x1, x2, and x3, I'm just going to leave mine as x, y, and z. I think it's nicer. Graphically, this constraint can be represented as a plane. I don't know how they expected you to graph a 3D region in the middle of an exam. It does say that they've given us the answer booklet to do that, but it's actually quite hard to visualize. Have we got any other constraints there? We've got non-negativity constraints. X is the number of questions answered from group 1, so greater than or equal to 0. Y is greater than or equal to 0, and Z is greater than or equal to 0. And we've got an objective function. So hopefully you're doing this problem after seeing linear programming at the level 3 NCA level. But we've got this objective function, which is the marks. And the marks, 4 marks, 5 marks, and 6 marks. So 4x plus 5y plus 6z is the thing we're trying to optimize, trying to maximize. Okay, let's have a look at the question. Write down the remaining constraints. We've done all that. And the objective function. What combination of questions should the student answer for a maximum grade, assuming all answered questions are correct? So I've made a GeoGebra diagram for this just so we can get our head around the situation. It's from the last video. I don't want to see that problem ever again. Okay, I took a long time to actually get all these constraints in the right perspective so that we could visualize it. I've put them in as equals because the boundaries are the planes, and it didn't want to shade in things for me. But the feasible region is this region that's right in front of us, and I can put in the non-negativity ones. Like z equals 0 is just saying that it's got to be above that purple plane, which is already in grey. Y equals 0 says it's got to be to the left of that blue line, and then the x equals 0 one says we have to be inside that thing, but that blocks it off, so I won't show that one. But there's the feasible region in that little wedge there. Okay, and then it seems like the red one's not actually doing anything. It's not really chopping off anything. So the red constraint is the total number of questions is equal to 100, but it seems like the orange constraint chopping through that tells you that it's not possible to do 100 questions. And it turns out the answer to this, the answer to the problem is actually 75 of group 1 and 15 of group 3. So you actually only answer 90 questions. You don't answer 100, otherwise you'd be on the red boundary. So the red boundary does nothing. Looking at the coordinates here, the coordinates at the mark schedule refer to A, B, and C here. It seems a bit strange that A and C are sitting 15 high when that there is actually the bottom boundary. But it turns out that 15 questions of the hard type must be answered because of the constraint that the student can't tolerate the basic questions, or too many of the basic questions, meaning that they have to do some hard ones. So we actually get another plane in there, z equals 15. Z equals 0 becomes z equals 15. Okay, and now our feasible region is now that little sort of wedge between the blue, the purple and the orange. You can just see the coordinate in the far corner is the coordinate B, 75, 0, 15, and that's the best answer. If you've done linear programming, you will have seen the sliding ruler method, hopefully. And so if I slide this plane, it's a sliding plane when it's 3D. Why is it not showing? Oh, because I have to actually put it in. So it's like this plane coming through here is the marks. Everywhere on the plane is the same amount of marks. And we're looking at what is the coordinate that it gets to last in the feasible region. And it looks like it's a close cut call between the far coordinate and the coordinate C. But it's got to C now. And I don't think it's quite yet got to B. It hasn't. So the optimal solution is that coordinate B, which was 75, 0, 15. Okay, you can't be expected to do that in an exam, obviously, but hopefully you enjoyed that little picture. Oh, my picture's just gone a bit haywire. Okay, so let's list out these constraints again. We've got x plus y plus z must be less than or equal to 100. That's the total questions. We've got 2x plus 3y plus 4z is less than or equal to 210. That's the time. We've got 2x plus 3y is less than or equal to 150. That's the time on the tedious questions. And then we've got the non-negativity. So just looking at that alone, if 2x plus 3y has to be less than or equal to 150, that's this dude, then 4z must be greater than or equal to 60. And z is greater than or equal to 15. Okay, if that blue thing is less than or equal to 150, then to make up the difference to get to less than or equal to 210, 4z must be greater than or equal to 60. So that tells us straight away z is going to be greater than or equal to 15. And then if we put those things in and into the first constraint, it tells us x plus y has to be less than or equal to 85. The total number of tedious questions must be less than or equal to 85, because we're going to do at least 15 questions of the hard type. And the thing that we're actually optimizing here is marks per minute, because the only constraint in here is time related. Of course the total number of questions as well, but we found out that didn't affect the answer. Marks per minute is the thing we're looking at. So if we go back to the question types, our objective function is this dude. You can't do this if there's constraints like amount of paper or other stuff. It's just time related, so you can. The number of marks type X, they give you 4 marks and they take 2 minutes to do. So marks per minute, you get 2 marks per minute. Type Y gives you 5 marks and they take 3 minutes to do. So they give you 1.67 if you get 5 divided by 3, 1.67 marks per minute. And then Z they give you 6 marks, but the time they take is 4 minutes, so that only gives you 1.5 marks per minute. So it's optimal to spend your time doing as much of the basic ones as possible. Do these first. Okay, so how many can we do? We can do as much as possible. we've got 210 minutes up our sleeve, but remember that we can only spend 150 minutes on these tedious questions. So we can do 75 of them. Do 75. Because 75 of those questions will take 150 minutes. Are there that many questions available to do? Does it say how many questions there are? It doesn't actually say how many questions are in each group. So we assume that there's enough to be able to do that. Okay, so if we do 75 of those, that means we use 150 minutes on the tedious questions. We don't do any of the moderate ones in group 2, and then the remaining time can be spent on the harder ones, because we have to do at least 15 of those. We've already used 210 minutes. No, we haven't. We've used 150 minutes. So we're using the remaining 60 minutes to do 15 hard Qs to finish. Okay, so the optimal solution is 75, 0, 15. Okay, and that's just purely a logic-based answer to that linear programming question. It's not having to look at the feasible regions and find the furthest point. Alrighty, we can apply logic to this critical path question as well. The mark schedule for linear programming goes into all sorts of iterative methods and whatnot. Very interesting, but not really stuff you can do in an exam. And the mark schedule for this makes it a lot more complicated than it actually is by drawing network diagrams and all sorts of stuff. If you've done critical path analysis, you know that you normally draw a network diagram, you do a forward pass and a backward pass, then you sometimes do a Gantt chart. But logic will get us through this. And I've just copied that Gantt chart in from the back of the mark schedule just to explain this, because it's a really quick way of communicating the information that we're given. So B can be started when A is a third completed. So A has a duration of 3. So after 1 hour is gone, B can start, and it's shown on the diagram there. B is starting. B cannot be completed until 1 hour after A is completed. Well, that information tells us absolutely nothing, because A goes all the way to 3 hours and B's still got 2 hours left. So it's going to not constrain us at all. B cannot be completed until 1 hour after A. We can just delete that. C can be started when B is a half completed. So B has a duration of 4. So half completed is 2. It's starting at 1. So when it gets to 3, that's when C can start. But C cannot be more than a half completed until B is complete. Okay, so C has a duration of 5. So, and it's starting at 3 currently on my diagram. That's the earliest possible. When we get to 2.5 hours in, C has to wait, because C cannot be more than a half completed until 1 hour after B is completed. So B finishes at 5. The 1 hour to 6 is when C can start again. Think something like, you can't apply your second coat of paint until the first coat is dry, that sort of thing. Then the second half of C can start. And then D can begin after A is 2/3 complete. So if A is a 3-hour duration, then D can start at 2. But can be no more than a half completed until B is complete. So when B is complete at 5, D2 could start there. However, it can only be completed exactly when C is 3/5 complete. So C is a duration of 5, 3/5 of that is 3. We've already got 2.5 hours accounted for in the first half of it. So another half an hour of C has to occur before D can finish. So D could start there at 5, but it would have an extra half an hour to wait before finishing. So you might as well start it a half hour late and finish it exactly at the right time. So D has to finish at 6.5. And then C, well, when we finish C, it's going to take us all the way to 8.5 hours. Okay, so designing a network to incorporate the constraints. I haven't drawn a network diagram, I've just drawn a Gantt chart. The critical path. The critical path is the first third of A, because we have to get that started on time. Then B and a waiting time. And then C2, the second half is C2. Those are the three things that have to be done in order, otherwise there would be delay to the network. The second half of A, can we delay that a little bit? Because it says that B can't be started until A is a third complete. B cannot be completed until 1 hour after A is complete. So we could take B all the way to 6. No, we have to have an hour waiting time. Okay, so B's critical. B has to start at 1 and finish at 5. If it goes beyond that, then C2 is going to get delayed, because C2, the second half of C, can't start until 1 hour after B is completed. So that waiting time after B counts as an extra hour of B, essentially. The rest of A2, it doesn't say anything about that, other than the fact that D can be begun after A is 2/3 complete. But the first part of D can go anywhere. It doesn't have to start at the earliest possible time. It's got some movement because C is not depending on it. So the second half of A can actually move as well a little bit. So yeah, the critical path of the events that have to go bam, bam, bam to not be affecting the total 8.5 hour time. If there's any delay in those critical events, then it will go beyond 8.5 hours.